Yeah. Hello, everyone. Welcome to today's seminar. It's my pleasure to introduce today's speaker, Professor Juel, who is a professor of fluid mechanics at the University of Manchester, and she has been the director of the Manchester Center for Nonlinear Dynamics since 2014. She obtained a DPhil from Oxford University in 1998, and she was a postdoctoral fellow at UT Austin and Manchester before her appointment to a faculty position at the University of Manchester in 2001. Her research focuses on fluid structure interaction, wetting, yield phenomena, biomimetic microfluidic models, and interfacial instabilities. And the last one is the topic on which she'll speak today. So I'll hand it over to Anne.
Okay, thank you very much for the invitation and the introduction. So let me get the slides started again. Yeah. Okay. So really, the talk I'm going to give today is about what I call propagating curved fronts in Healer-Short channels. And here, what you can see are three air bubbles, and they're propagating in a steady formation, but the longer finger-like bubble is oscillating, and so this is a system which confined between two closely spaced glass plates, and you're looking down at from the top at these bubbles, these basically pancake-like bubbles in the system. And this so this type of system exhibits an incredible wealth of dynamics and pattern formation, and has the advantage of being really simple, where the physical ingredients are really simple. And here, really, geometric confinement is going to dominate the proceedings. And so what I want to do here with this talk is maybe focus on a mostly missing link, which is between the sort of pattern formation we observe in these systems and the actual dynamical processes that form these patterns. And in a sense, I'm not going to get very far, but I'm going to look essentially at time periodic states, or try to look for time periodic states, and I explain why I want to do that. So oops, yeah, I just need to find my my slides. Okay, here we are. So as I said, the complex pattern formation is really quite ubiquitous in viscous fingering problems, and here you see some examples, some typical examples of that. So in particular, the process is one of diffusion limited finger growth. So what you're looking on the top left is a radial Healer-Short cell. So you have two parallel plates, and you have an injection hole in one of the plates, and then you fill the narrow gap between these two plates with, say, oil, a viscous liquid, and you inject air. And when you inject the less viscous fluid through the central hole with, say, a constant flux, then you get an initially circular interface that's unstable to viscous fingering, and then you can get repeated cycles of finger growth, tip splitting, and competition between fingers. And so this, I would argue, is a form of disordered front propagation. And the reason it's disordered, it just doesn't settle down in time. And there are some caveats to this because of the size of the cell, but that's the general idea. In all the examples I'm showing on this slide, you essentially have systems where injection is with one typically less viscous fluid into another sort of in the confined space. And essentially the fingering that you see in all these systems follow the path of least resistance. Now, there's been much recent interest, and you have these beautiful pictures in a variety of systems. Here's dense suspensions. Sorry, I need to use my pointer, I think. Dense suspensions up here. This is fingering in liquid crystals. This is failure modes in dense suspensions. And there's been, and the nice thing about viscous fingering is that you have a nice tool in which you can essentially explore the sort of mesoscale rheology of the material with this type of simple two-phase flows. But the complexity, you don't need all this complex rheology. All you need really is complex confinement in order to control your viscous fingering. And that's really what I want to probe in this talk. And it can, with the idea that it can provide a route to understanding key mechanisms behind the pattern formation. And so the question we're asking is really, how do these sort of patterns form dynamically? So this disordered pattern formation, or if you now replace the top lid of the Healy-Shaw cell with an elastic sheet, then you can totally change the type of pattern formation that you observe. Okay, so what are the typical ingredients in this, physical ingredients in this system? So we're going to look primarily at systems in a channel. Oops, I need to move that down. At viscous fingering in the Healy-Shaw channel. So what you have is two parallel plates. You fill the gap between the two parallel plates, which are such that the width, the aspect ratio width over gap thickness is much greater than 1. You fill the gap with oil, and you inject now air, say, from one end with a constant flux. So in a system like that, you have no gravity, no inertia. And essentially, the physics are reduced to the injected air working against viscous and surface tension forces. So the natural parameter here is a capillary number, which essentially gives you a measure of the ratio of viscous to surface tension forces, and it tends to be proportional to the speed, a characteristic speed in the system, say the speed of the fingers. And what's really useful in what makes the pattern formation so complex in this system, and makes this system so interesting as a sort of as an example of pattern forming system, is because they're all here. The nonlinearity of the system doesn't sit in the oil. That's purely Stokes flow. You have all the nonlinearity arises exclusively at the air-fluid interface. And what's nice also is that the whole system is very amenable to numerical modeling of a 2D depth of average lubrication flow. So what you're seeing is essentially you start with a flat interface and you inject fluid, and then that interface is then linearly unstable, and so you get a series of fingers, and then these fingers will grow and they will compete, and eventually at long times you end up with a single finger that's steadily propagating, and you see it in the experiment because it's stable. And this is sort of result that goes back to Safman and Taylor in 1958. So now it doesn't stop there. Essentially, really, in terms of parameter, we have a Safman-Taylor parameter, which is the aspect ratio squared times this capillary number, and the single finger can be shown to be linearly stable for all values of this parameter, which is so alpha squared times capillary number. And so, in fact, much of the early work on Safman-Taylor fingering was concerned with what's called the so-called selection problem at infinite capillary number, so at zero surface tension. And that is because there's an infinite countable family of Safman-Taylor finger in that limit, but surface tension then acts as a singular perturbation to select the one we actually observe, so like this one. And there's lots of interesting mathematics to be done in that limit. But from an experimental point of view, we operate at finite capillary number, and we say that essentially we'd like to understand the pattern formation in that sort of intermediate regime where surface tension is essentially finite. So And an interesting observation is that if you keep in practice in your experiment, you get this finger that is steadily propagating, and then you keep on increasing this Saffman-Taylor parameter. Eventually, you're going to get a relatively abrupt transition to disordered front propagation, just a little bit like what I showed you in the radial system. So this will happen at sufficiently large Saffman-Taylor parameter, but that threshold, if you like, will depend on the level of background perturbations in the system. So it really has all the hallmarks, if you like, of a subcritical transition. Now, when you so you could argue that in a sense that transition will happen typically at a finite value of the Saffman-Taylor parameter, and so it makes no sense if you're interested in this. Well, it doesn't make a lot of sense if you're interested in, certainly from a practical point of view, in this transition to go to these very large Saffman-Taylor parameters for that particular set of dynamics. Now, what's interesting here is that when you go to this, what I call disordered front propagation, then you have a continually evolving pattern formation. So if you want to have any chance of understanding how this system behaves, then you probably want to go and look at sort of a dynamical systems approach to this, where essentially the where you can basically sort of focus on transient dynamics that happens in the system. And so if we do that, so if we think a little bit about what a dynamical system approach would look like, then we'd say, well, we can look at a really simple conceptual picture of this. And transient dynamics typically is key to understanding continually evolving disordered propagation. And it's because essentially when you have a nonlinear system, then like this one, where all the nonlinearity sits in the interface, but then during transient evolution, the system tends to be strongly influenced not just by this stable states towards which it may be converging, but by all the weakly unstable states of the system, those that you only see fleetingly in experiments, but that are there nonetheless and that you can calculate theoretically. So if you take, for instance, the sort of simplest example of a weakly unstable state, it would be like a saddle, or in case of the fluid dynamical example, it would be stagnation point flow, like this stagnation point flow, where the stagnation point is here. And then in that case, you have stable and unstable manifolds, so a stable manifold here and an unstable manifold there that divide the streamlines of the flow. And so you can be essentially transiently attracted towards the fixed point, but eventually you will always be pushed out again along the unstable direction. And so here in this simple example, stable and unstable manifolds are, to say, the dividing streamlines of the flow, and the ultimate fate of any fluid particle is going to depend where you start. So if you start in this quadrant here, then you're going to be attracted this way and then pushed out that way. And so you can think of these manifolds as the invariant objects, and we often refer to as invariant objects that are essentially in phase space and that direct the flow of the system. And so often in the sort of dynamical system literature, they're referred to as edge states. And this is a sort of simplest iteration of an edge state. And so why are we interested in this? Because basically, when we see continually evolving system that performs complex dynamics, then it's likely that these complex dynamics are triggered or are sort of actuated by a set of edge states in the system. So manifolds or invariant sort of objects that are related to weakly unstable states of the system. And so the key example for this is the nonlinear dynamics of transition to turbulence in shear flows. And there, that's been very that their dynamical systems has provided a very successful framework to understand this transition, and this is really a huge field, and it's also a much more complex system than the one we are looking at. But essentially, in that case, you can get multiple unstable invariant objects present in the system, and you can get very complex dynamics that results as the sort of as you get sort of transient behavior of the system that move between these complex invariant objects. And what's been found in these types of system is that what the key sort of modes are unstable traveling wave modes, and they're key to the transition to turbulence, and these are essentially periodic states. And the idea is that basically the manifolds of these periodic states, so if they are unstable, they will have, say, in a large dimensional sort of phase space, you will have many stable directions and a few unstable directions, and you can entangle all of these stable and unstable manifolds and give you a complex essentially edge state that then separates laminar and turbulent flow. That's called the edge of turbulence. So we know nowhere near the complexity of these 3D Navier-Stokes equations, and in a sense you can say that's kind of an advantage, because we can actually carry out direct numerical simulations quite easily of our 2D depth average model to look at exactly what the basic dynamics that occur in the Healy-Short channel are. Okay, so really the question that I've sort of been trying to motivate is really, do we see periodic modes in viscous fingering? And if we do we see them as stable periodic modes or unstable periodic modes? But is there a propensity to create more complexity than the very simple one stable, steadily propagating finger that you normally see when the system is not disordered? And so for that, you can go and look at some numerical simulations of the system of a propagating finger in the Healy-Short channel. And here we're plotting the width of the finger and the speed of the finger as a function of the capillary number. And these are two decent measures which of the steady state modes of finger propagation. So what we find if we do numerical calculations of this is we find our symmetric mode as a function of capillary number, and it will take slightly different speed, say, relative to the mean speed in a channel or width, but it exists over the whole range that we're looking at here. But what you also see is and it's stable. But what you also see here are these dashed lines, which corresponds to unstable modes. And so you'll have this double-tipped mode and this triple-tipped mode and this asymmetric finger. So there's a whole host of weakly unstable fingers, but these are only ever seen very fleetingly in the experiments. And so really, is that it? This is a steady bifurcation diagram. But there's likely to be more unstable time-dependent modes of propagation. So can we get some idea about the sort of more general dynamics that goes on in that system beyond these steady states, and because that would give us a hope to build up enough complexity to drive disorder. Okay, so actually, if you go back to the 90s, there were a series of beautiful experiments around Yves Couder, where the fingertip of a Saffman-Tailored finger was systematically perturbed, either with a small bubble at the tip here, or a stretched wire along this system here. And that alters the curvature and of the front essentially alters the curvature, the tip of the finger, and it leads to these time periodic modes. So here the tip is pulsating periodically, and here it's alternating, pulsating alternatively to the right and to the left. And so essentially it leaves essentially the spatially periodic pattern behind it as a result of the dynamics of the tip. And so the question sort of that then springs to mind is that, well, okay, you can clearly then, by manipulating the finger, sort of stabilize some of these alternative propagation modes. But how generic is this time periodic behavior? Is there really a mechanism, generic mechanism for time periodic behavior in these systems? Okay, so for that, what I'm going to show you is two related systems. So the first system is so the first system is a system where we're propagating a finger in a Juel short channel, but the Juel short channel now has a top elastic lid. And that's the one on the left-hand side here. And really the idea here is that I want to explore the general landscape of these Juel short channel, and then explore the propensity for time periodic behavior in these systems. And that's why I want to use two related systems, but where I've sort of altered the geometric confinement or perturbed the geometric confinement compared with a constant depth channel, which is a bit boring because you only ever see a single steady finger propagating in it. So can we get some insight by looking at these slightly more complicated systems? So that, as I said, the left-hand side one, we've just changed the regular channel to a channel with a top elastic lid that can therefore deform. And the second system I want to look at is one where we have essentially a rigid Juel short channel. We're going to essentially perturb its confinement by adding a small rail, and the rail height is on the order of a percent, actually 2% of the total depth of the channel. So it's a very, very small protrusion down the center line of the channel, as indicated by this orange line. Okay, so these systems are so closely related that we can really model them with very much the same model as we would use for. So it says here that my internet connection is unstable, but hopefully that'll. You can still hear me, yeah?
Yes.
Yeah.
It's just okay, I think.
Okay. Okay. So let me know if it gets worse. Yeah. Okay. So basically, we can use a depth average lubrication model, and here the idea is essentially that we've taken a Juel short cell and we're imposing a prescribed geometric or time evolving variation of the channel depth, which is this B. So prescribed, that could be, for instance, when we have a rail in the channel, and time evolving is when we have an elastic lid, and then in that case, as we reopen the channel, the height of the channel changes as the channel inflates. So the general framework is we need some depth, so we can take the Navier-Stokes equations and apply lubrication approximation, and that by depth averaging we will get the Reynolds lubrication equations in their most general iteration. And so we essentially get equations where this B, so this B, the height of the channel, comes in to the bulk equations of the governing the oil, and then we need a set of boundary conditions. So we have kinematic boundary conditions And then we have dynamic boundary conditions that in the limit of a large aspect ratio channel and limit of the lubrication approximation essentially reduces to the Young Laplace equation. And the difference here to the usual Young Laplace equation is that we have a term for the in-plane curvature. So we have the pressure difference is proportional to the across the interface is proportional to the curvature. So that's a sum of the in-plane curvature, what the pattern we look at from the top, plus a term that incorporates the transverse curvature across the depth. And normally we can sort of absorb that into the pressure difference because it doesn't vary in the constant depth Healy-Short channel, but here, because it varies in some prescribed way, it has to be incorporated, and there's a significant term in this relation. So essentially, what you can so that's what you do for the fluid dynamics in these channels, and then you have an elastic lid. You also need to model for the deformation elastic lid, and we use the Foppel-von-Karman equation for elastic sheet, and we couple that fully to the flow problem. And really, my object here is not to give you details of there's lots of complexity in implementing these models, but I really just want to give you the sort of the physics. And so here you have essentially depth variations that are going to affect the force balance, which corresponds to the injected air working against viscous and surface tension forces. And by having a variable depth, then you get some mobility in essentially Darcy's law. So essentially you get you get some changes in mobility in Darcy's law. So essentially you get increasing viscous resistance in the converging channel, and you also get surface tension forces, which becomes increasingly large as you go into the convergent channel, say, because the curvature, the transverse curvature increases. Okay. So you can then apply, you can sort of formulate all of this in numerically, and we use UMFLIB, which is a sort of homegrown finite element library developed by Andrew Hazel and Matthias Heil in Manchester. And we so this is all implemented in C++, and we have a mesh, as you can see here, that deforms with the interface of the bubble. It's a finite element, finite element library. And essentially what I want to point out here is what the capability that gives us rather than the details of the implementation. And essentially we can do direct time simulations, we can do steady state calculations and parameter continuations. So I've already shown you these examples of this with the bifurcation diagrams or in the different bubble states that we could find. We can do linear stability calculations, test the stability of these, and we can also do something called edge state tracking that I may mention towards the end. Okay, so we've got a good set of tools, and we can get started on looking at the channel, the Healy-Short channel with an elastic lid. And essentially, if you think of this system, then we have, if we just put a flush elastic lid over a rectangular channel, then we have pretty much the same system that we started off with, but the only difference is the fact that the lid can inflate as the air flows into the channel. So essentially, rather than having, when we inject air, the air just working against viscous and surface tension forces, we now have the air working against viscous, surface tension, and elastic forces, so resistance to deformation. And so if you look from the top, you see pretty much the same as we saw in the rigid channel, but the difference is really in side view, where you can see that the air bubble is inflating to some extent the lid of the channel. And there's a and that can be measured in the experiment, and you get where you can plot out sheet deflection, this line here, as a function of distance, so relative to the, say here, the interface is at 0. So the airflow is coming from the left, and you have the interface about here at 0, and you have a steep deformation of the elastic sheet on top, and then far ahead you have an undeformed oil layer. And so all the action in this system takes place, really, all the fluid dynamics take place in this fluid wedge right ahead of the interface. And it's the size and the form of this fluid wedge that to a large extent determines how the system is going to reopen. And we can add some complexity to that, and to make it akin to pulmonary airway reopening by, in addition to having an elastic lid, we can also, in principle, change the shape of the cross-section, the initial cross-section, by collapsing the top membrane. And so this would be, if you think of the airways of the lungs, if you think of the lungs as a branched network of elastic channels ending up in the alveoli, where gas exchange takes place, then each airway is essentially an elastic tube that is fluid lined, and then under certain conditions, say during the birth of a child, the lungs, the airways will get strongly collapsed, and if you collapse a circular tube in the simplest geometry, then you get typically these two-lobed configurations, as shown here. And our model, essentially, in our model, we can do half of that channel, if you like, by collapsing the membrane, and we get something quite similar, but we introduce thereby a new parameter in the system, which is the essentially the initial cross section, so the ratio between the collapsed cross section here and the neutral cross section, which would have been the rectangular one. Okay, so we can take that system, and we can look at, in particular, we can sort of play around and we can play around with that system, and we can in particular demonstrate the importance of the curved front, and you know, and what the effect of having a curved front is, and in particular what you're looking at on on the left hand side is the sort of okay, so let me start again. So typically when we talk about fingering, we always start with a flat interface, but a flat interface in a channel isn't something that's possible to create, because you always have boundaries, so you can't create this idealized system. But in this elastic sort of channel allows us to play around with the channel cross section. And here, if we put a sort of quite a large obstacle and make a thin channel with large ditches on each side, then we can essentially create something that is very close to a flat front in the center of the channel. And then when we do that, then we get these stubby fingers that are propagating steadily along the propagation direction. So a front with these steady small fingers. And this is very analogous to, say, the peeling of a film, where you get a steady pattern for moderate capillary number. And here's the movie I've got is, I need to get out the laser pointer, I think. Oops. Yeah, the movie I've got is not quite as steady as that. There's some dynamics going on in there. But you can see essentially that there's minimal sort of, there's a little bit of you essentially get a steady front propagating, relatively steady front propagating down the channel with a number of fingers that that have some internal dynamics similar to what you will see in something called a printer's instability, when this McCune and Taylor peeling system at sufficiently large capillary numbers. But essentially, by having a flat front, you get a steady instability, initial instability of this front. Now, if you move to a curved front, and you can do that by avoiding having this engineering, if you like, the cross section of your system. You start with a curved front, and then you get a very different type of behavior. So you get, you still get fingering in this system, very different from what you get in the rigid system. And what you've done here is just changed, compared to rigid system, made the top lid elastic. But you get essentially still this fingering at the tip, but now that forms, if you now sort of superpose all these, the fingers as they grow, and you look at the time sequence of that, which you're doing on the bottom, you can see you get a really complex set of pattern formation. And this is really due to the fact that you get advection of these tip perturbations down the side of the channel, at least to some extent. And you can look at that a little bit more closely, because you have a kinematic condition that tells you that essentially the way this works is that you at the interface, each fluid particle is going to propagate normally to the interface. And so as a result, any initial perturbation of the interface as the finger grows forward is going to be advected sideways. And so, oops, I keep on clicking on this, sorry. And so what you can do is that you can sort of say, okay, let's consider the envelope of a Safman-Taylor finger, and look and put all the points around this envelope and give them their direction normal to this envelope as it propagates. And then you can predict what the computed trajectory of any small perturbation or a point on the finger is going to be. And essentially you find that the computing trajectory corresponds very nicely with these sort of fjords that you find in the final pattern of the sort of time sequence of the movie. So essentially, this kind of gives you an inkling of the fact that every time you have a curved front as opposed to a flat front, you're going to get advection of the perturbation, of any perturbation or any point on your interface, and that's basically going to get advected sideways as the finger moves forward. And so so that sort of gives you the beginning, in the sense of an unsteady mechanism for the propagation of a front. So essentially, for unsteady propagation, you expect that you need a tip instability, and then the features of this tip instability then are then coupled to the advection around the front, and that gives you naturally an unsteady propagation mechanism. And actually, if you now look at, say, you choose a certain level of collapse and you inject air at constant flow rate, and you do it for increasing flow rates, so this increases the capillary number here. Essentially, what you see is that you get a whole host of different complicated dynamics, much more complicated, again, than what you would see in the rigid channel. So you start with a sort of rigid channel type, simple symmetric fingers up here. Oops, I need the laser pointer up here. And then as the capillary number increases, you basically get to more and more complex dynamics. And so this is directly linked to the sort of mechanics of reopening in these systems, which depend on the size of this fluid wedge ahead of the finger. But here, I don't want to get into all the sort of subtleties of this mechanism. Suffice to say that essentially, as you increase the capillary number, the amount of fluid ahead of the finger typically decreases, and you get less and less effect of viscous forces. And instead, so at low capillary number, you have a balance between viscous and surface tension forces, a bit like in a rigid channel. So you get fingers a bit similar to that, because you have a lot of fluid in front of your fingertip. As you increase the capillary number, then there's less and less fluid in front of your fingertip, and you end up in a situation where really you have a competition between elastic forces and surface tension forces, and viscous forces really become very minor in setting this reopening of the channel. What that means is that you go from, for us, and the only thing that really is important here in terms of the instability is that what you start with quite a narrow finger, and as you increase the capillary number, the finger gets wider and wider. And as it gets wider, then the tip gets flatter. And as the tip gets flatter, it gets prone to tip splitting instabilities. And then eventually you get this really rather complex small scale fingering on the tip. So essentially, as you increase the capillary number, you get a system that is more prone to tip instabilities, and these tip instabilities in turn get affected, leading to unsteady dynamics. And you can sort of calculate all of this numerically, and you can see that here what we're doing is that we're looking at the sort of pressure of the finger, the air in the finger that is propagating in this elastic channel. And we're looking at it as a function of capillary number for a given initial level of collapse. At very low capillary number, we have these nice symmetric fingers here, and then we get some variety of transition. And there's really quite a rich bifurcation structure that can be calculated numerically with a set of pitchfork and hop bifurcations. But essentially at low capillary number, we get very good direct quantitative agreement with our model. Whereas then as we increase further, we get multiple steady states. And one of these steady states is a very good envelope to what we observe experimentally. However, experimentally, our system has become unsteady. And of course, that's not captured by these steady solutions. And it turns out that all of these steady solutions by that time are unstable. So you may ask, well, what's the role of all these unsteady solutions at that point? Because really what you see in practice is very, very far away from well, the detail is very far away from the simple steady solution. However, what's kind of interesting in this system is that you can basically predict overall the stuff. If you just want to know what the pressure of reopening is, then the pressure of reopening is very well captured, remains very well captured by the steady solutions. But if you want to know the dynamics and the pattern, well, or the pattern formation, then you really need to start understanding the dynamics of the system. And really, this is just to sort of emphasize this a bit further, that really in terms of, so we can look at this, the bubble pressure as a function of level of collapse, and again here at reasonably unperturbed initial cross section of the channel up here, then we're very much in a similar system to the rigid heel-shore system. But then as we collapse the system further, we go through a variety of bifurcations, and again you have two Hopf bifurcations. So really time dependence is ubiquitous in this system. And actually, if you just look in between these two hops, if you look at the spectrum at that point, you have, and this is very typical of this Saffman-Taylor system, you have a whole sort of set of near marginal complex conjugate eigenvalues, so whole families of these near marginal complex conjugate eigenvalue, and you have very clearly advective tip instabilities where you get periodic cycles, even for very weakly collapsed channels. Okay, so what have we learned? Well, we've in a sense we've perturbed the system quite significantly. You could argue by changing the top boundary to an elastic lid, and we find that actually that is a very good mechanism for generating time periodic and unsteady behavior in that system that wasn't sort of so clearly apparent in the rigid Healy-Short channel. And really the question is there a generic sort of time periodic mechanism in viscous fingering that makes that makes it easy to always get these time periodic or more complex unsteady behaviors? And for that we return to simple depth perturbed rigid Healy-Short channel. And I'm just okay. We return to the depth perturbed one, and we look at this system where we have a rigid channel with a thin rail, and that's easy to destabilize. So here's an example. If I can, whoops. So here's an example. You get a little bubble. You can see that it spontaneously destabilizes. And here, in this case, is very much the tip of the finger that keeps on essentially falling over the rail. And you can do this numerically as well. So these are kind of neat mechanisms in a sense, because they're oscillations in the absence of any inertia. And it's really just an effect of confinement. But in this case, and I'm not going to detail that because I'm running out of time, the rail is essential, because essentially what you're looking at, the rail here in the middle, and it's a generic mechanism by which the finger falls over the rail and advects this tip instability. But you can also go to the system that I showed you right at the beginning, when you had the 3-bubble formation, and you can stabilize this formation in the system with the rail, but you're not directly relying on the rail for the instability. It's a sort of indirectly stabilizing this formation, and it's the medium bubble here that interacts with the trailing bubbles and changes the shape of its front. And so essentially you get some form of remote actuation, and you see that you generate these very very regular oscillations on the bubble. And if you look at this a little bit further, then you can start from rest, and you can look at these oscillations that then grow in time in this sequence here. And if you plot this in some way, then you can see that the oscillations grow in time and then eventually saturate. So it reaches a sort of steady state of oscillation. And we can characterize this because by fixing the leading and the trailing bubble, we can actually, and just changing the size of the middle bubble, for instance, that's one parameter we can vary. And we find that it has all the hallmarks of a Hopf bifurcation. But what we're interested in here is really what's the oscillation mechanism. And we're back here to basically somehow being able to actuate the tip of the finger. And by having it in this 3-bubble formation, the middle bubble changes applies a pressure perturbation to the tip of the trailing bubble and creates this flattened interface. And a flattened interface in viscous fingering is always unstable, and then it creates this essentially fingering instability at the tip. So that creates this dimple here that grows, and then a fjord develops, and then the two fingers compete, and then you get the primary tip that widens again and restores itself to its original conformation. And so that gives you essentially an oscillation of the tip that is simply due to the presence of the middle bubble. So you have essentially, so the question is really, okay, so we can see exactly what creates the perturbation of the tip, but now what is then involved in restoring the interface? So what makes this an oscillatory mechanism? And so you have a competition between the induced tip splitting instability and the natural tendency for the disturbed interface to restore as the finger or as the bubble advances. And so you can actually show this in this sort of system. You can show this very, very clearly. So you can measure, for instance, the typical wavelengths, if you like, or some characteristic length of the tip instability on the side of the bubble. You can plot that as a function, say, our parameter, the side of the middle bubble. And you can plot the time it takes, so the whole period of this oscillation, the time it takes to restore the interface, and you plot that here. So these are non-dimensional quantities, suitably non-dimensional as quantities. And then you can see that if you now, essentially that your disturbances are essentially advected at the speed US, so you can measure the speed US, and you find that the advection speed of the perturbation of the tip, and you find that lambda over US and tau are essentially the same quantity. So essentially, you have the period of the oscillation is set by an advection, is set by an advection speed. And then you can say, well, okay, so how does this advection speed depend on the propagation of the bubble? So you can fix all three bubble sizes and just vary the flow rate, and you can look at UB, the bubble speed, and US, the advection time, and you can see that they increase reasonably similarly to leading order, at least with the flow rate. And actually, if you start looking at the time scale of the period of the oscillation, you find that it actually decreases linearly with UB for increasing fluxes. And that essentially tells you that there's nothing in this. You don't need a particular time, an additional time scale in this system. All you need is just restoral set by the finger speed in the channel through the usual force balance. And so essentially you have a tip instability, and then the fact that the finger propagates is enough to restore your interface. So this is a completely then generic mechanism that's present in all of these systems, where the tip finger, the tip instability then followed by restoral through just simple tip propagation. And that means that time dependence and unsteadiness in Saffman-Taylor is totally generic. I think I've already reached this. Yeah, I'm well past. Yeah. So I'll just show, just before concluding. So I had one more thing, but I'll just show you one more movie before concluding. It's kind of fun, and then I'll stop. Whoops. so that's a good time to stop, because I've been a bit slow in the beginning. And so what I'm going to show you is really now, what about, disorder and unpredictability in these systems? And I just wanted to show you 2 movies, if I find it. So typically, again, if you want to get a handle experimentally on complex dynamics in these systems, so here I've just sort of been interested in finding out about, where does time why is time dependence and these so complex dynamics so ubiquitous in heat ashore. Now, the next thing you would want to do is start looking at these more complex dynamics. But if you go to high fluxes or high flow rates, then you can start the same bubble with exactly the same bubble 5 times over, and you end up with completely different outcomes. But in a sense, you say, well, that's not so surprising, because you have reasonably high flux and the system's very sensitive to any small perturbations. But interestingly, you can also do this at low flux. And so here I've got, So here, basically, you're looking at a bubble in a system I'm going to perturb with a little obstacle. And the three bubbles are exactly identical. But you can see that the outcomes, the long-term outcomes of what happens after they've been perturbed, is completely different. So you get a symmetric bubble, an asymmetric top, and an asymmetric bottom. And you can do that further, and you can look at these 2 bubbles. Again, same bubbles as the 3 top ones, and these ones, so they seem like to be oscillating a bit, and then they split. And in one case, they rejoin, and the other case is separate indefinitely. So essentially, and this is at really low flow rate, and again, it involves oscillations. As you see, the system starts oscillating after it's sort of been perturbed. But essentially, it means that for all intents and purposes, the outcome, even at low flow rate of what the bubble's going to do in the long term, is unpredictable to within experimental resolution. So with that, I'll just finish and tell you that I've shown you some how I've tried to show you that time periodic behavior is really generic in any curved front propagation due to the advection of tip instability and interface restoral by a viscous finger propagation. And you really see time periodic behavior in classical viscous fingering, certainly not simple ones, but the manipulation of the geometric confinement can easily generate unsteady pattern formation in these systems. And then what I just sort of gave you a glimpse of is that you can also have these practically essentially unpredictable long-term outcomes which manifest in even perfectly simple ordered systems at really quite low flow rate. And really the outlook is really, are these unstable periodic modes of propagation essential for complexity and disordered front propagation, a bit like what has been found in the transition to turbulence, and do they actually occur in a simple Saffman-Taylor fingering situation? And then really the big question for me that I'd be interested in finding out is really whether in such a simple system, which really has so few ingredients, can the disorder really be self-sustaining, like in shear flow turbulence? So does it always remain transient? You always have to kick the system with noise in order to retain the unsteady front propagation. So with that, sorry if I've run over a little bit, and thank you for your attention.
Oh, no worries, and thank you very much. It was a very interesting work and some cool pattern formations there. I've never seen those before. So there's applause from a couple of audiences. That's good. I'll open the floor for questions. If you have, please go ahead, unmute or type it in the chat and I'll read it out.
Anne, I could ask a question.
Sure.
You did have in one of your slides some eigenvalues.
Yeah.
I think these were for the sort of multi-tipped configurations that might have been on that slide. But for them, or for any of them really, how do you determine these eigenvalues? It's a numerical exercise, I guess, but can you just sort of give me a sense of how you do that?
Hold on 1 second. I'll bring it. Sorry, I'm trying to bring up the relevant slide for you. Yeah. So in these systems, so this is the slide I think you referred to. Yeah. So basically, we calculate the steady states for these systems, and then we calculate the eigenvalue spectrum using, a sort of, in the eigenvalue spectrum from the Jacobian. So you calculate a certain number of most dangerous eigenvalues.
So these are just like as many equations as you have nodes in your finite.
That's right. So you get that exactly. So it's a discretized system that has therefore ends up having a very large number of degrees of freedoms based on the mesh, and then you get basically an eigenvalue associated with each point. Yeah.
And this is how you can characterize them as being weakly unstable.
That's right. Yeah.
They look almost stable, but not quite in terms of these numerical.
Yeah. So I honestly don't know how this relates, but it's something we found in all the Sackman-Taylor calculations we've ever done, be it these ones with the elastic lid or the rigid ones. There's always these families of. That's really intrigued us for a long time. Why is it that there's always these families of near marginal complex eigenvalues?
And for the single finger, they're all got negative real part, or
yeah, they all have negative real part. And this is not an unstable periodic orbit. It really just is a family of these. Mm-hmm. Yeah, but there seems to be huge numbers of them. So clearly, time periodicity is something that's quite generic to this system. It's another way of another piece, if you like, of evidence in the puzzle.
Any other questions? And I had one. How do you introduce the perturbation experimentally right at the tip of that pattern?
At the tip of the so was that for these experiments? Yeah. Oh yeah. My student actually did that. It's a shame I should have brought up. There's a really beautiful. He sent me a really beautiful video. So the point is that if you put a little bubble in front of a finger, the bubble moves much more slowly than the finger. So you can put the bubble quite a way ahead, and the finger will always catch up with it.
Oh, okay. All right.
So that's how you do it. And actually, if I had that, probably take. Let me see very briefly if you can. The movie is really very nice. If I found it, but I suspect that I won't. So you can do that very, very easily. Yeah.
All right. Okay.
Thank you. I don't know what it is.
No worries. That's all right. Ivan has a question. Go ahead, Ivan.
Yeah, hi, and thanks for your talk. Just curious, when you do your simulations of the case with flexible top, do you have to solve the fluid structure problem, or is it just a matter of having a wedge?
No, we solve the whole thing.
Okay.
So it's a fully coupled. It's a fully coupled system where essentially it's controlled by the volume flux. So you have we do a lot more than I said. Basically, it's a lot more involved. So okay, so let me when we do with the top on, we fully couple the Foppel-von equation, but then it's all coupled to the system via the mass conservation in the system. Yeah.
Okay.
So we have a finite. It's under constant volume flux injection. But what we also do in those simulations for the ones I showed here, in order to, this is not easy to get. This agreement is not easy to get. If you just did couple the Foppel-von to lubrication model, you wouldn't get anywhere as good an agreement. What really is underlying this is that we also have to take into account the thin film of liquid that's left behind the finger as it advances. So the liquid is wetting the channel, and it leaves the thin films on the top and bottom. And these are taken into account in a sort of slightly ad hoc manner, but a fairly successful ad hoc manner based on what is done, what can be calculated in rigid channels. And so we essentially adjust the mass conservation in the system by imposing these passive layers of thin films that have a particular dependence on capillary number. And when you do that, then you get the right finger width and all the rest of it.
Thank you.
I have a question as well. Thank you so much for your presentation. It was awesome. I'm going to have to go and have a look at your JFM papers, and if I may, I'll hopefully contact you in the future if I get stuck, because this is just awesome work. My question kind of follows on from Ivan's a bit. I'm curious about the contact angle between the two surfaces, the upper and lower surface, and have you tried different films that produce different contact angles?
No, yeah, so we don't. I mean, so you mean the contact angle between the
solid, liquid, other fluid?
Yeah,
interface.
Exactly. So this is. I mean, so we haven't, because it's a bit of a mess, and so, and you would then, typically you would have, so the people who've really looked very, very nicely at in fingering in recent times at true liquid systems is the no, I don't have a picture here, but it's Irmgard Bischofberger, who's also doing the liquid crystal fingering. Basically, we have essentially our oil is fully wetting. Mm-hmm. So it wets the top and bottom, and the air is essentially completely de-wetting. So there's no really, we avoid wetting at all costs in those systems, the experiments we've done for simplicity. However, you could, of course, have much more partial wetting, and you could also be put yourself in configurations where you're more like in an imbibition configuration, where the viscous fingering mechanism is less important.
Right. Yeah. I have some related work to this that I'm doing, but I think Paul Brander would kill me if I let on about it before it was published. So maybe I should chat to you at another time about it and share a video, because it's highly related and super interesting. So thank you so much for this presentation too. It was fantastic.
Great.
Thanks, Patrick. Any last questions? No? All right, then let's join me in thanking Anne. That was an excellent presentation and an amazing work. Thank you very much.